Welcome to the Code Mental channel. If you don't know me, my name is Armindo and I'm a software developer, and my channel is all about software development and Python programming. So, in this episode, we're going to be taking the second module of deep neural networks. Last time, we did the module 1, which was a single neuron. You can also find in the channel if you haven't taken that course yet. So let's get started. In this lesson, we're going to see how we can build neural networks capable of learning the complex kinds of relationships deep neural networks are famous for. The key idea here is modularity, building a complex network from simpler functional units. We have seen how a linear unit computes a linear function. Now we'll see how to combine and modify these single units to model more complex relationships. Layers. Neural networks typically organize their neurons into layers. When we collect together linear units, having a common set of inputs, we get a dense layer. So, if I understand well, just kind of neural networks. So when it mentions layers, we're talking about, hang on, so I think this is one layer, so this is a dense layer. A dense layer of two linear units receiving two inputs and a bias. I think I need to just revise what was a linear unit, so I'm going back to the previous course because I kind of forgot. So linear unit. So a neuron is a linear unit. Linear in the sense that it's basically using this function here, y equal to wx plus b, because this actually is this is an equation for a line. If you look at the x in a two-dimensional plane like this, and then you have the curve something like this. So the linear unit is basically a function which is a linear function, so it's actually a line that goes either. So if the bias is 0, then it goes through the origin. If the bias is, for example, 1, it goes through like y equal to 1 and so on. Right, so going back to where we were. So when it talks about two linear units, these are two linear units. So if the two linear units have the same common inputs, then we get a dense layer. So it's starting to make sense, right? So the idea is, okay, so I pass in x0 and x1 to the linear unit 1, right? And that gives me y0. And then I pass in the same two inputs to the linear unit 2, and that gives me y1. So that's why they call it dense layer, because it uses the same set of inputs. That's what I understand at least. Right, so you could think of each layer in a neural network as performing some kind of relatively simple transformation. Through a deep stack of layers, a neural network can transform its inputs in more and more complex ways. In a well-trained neural network, each layer is a transformation, getting us a little bit closer to a solution. Many kinds of layers. A layer in Keras is a very general kind of thing. A layer can be essentially any kind of data transformation. Many layers, like the convolutional and recurrent layers, transform data through use of neurons and differ primarily in the pattern of connections they form. Others, though, are used for feature engineering or just simple arithmetic. There's a whole world of layers to discover. Check them out. Okay, convolutional. We've heard that, I guess, we all might have heard that if we learn about AI and convolutional. What is a convolutional layer? 2D convolution layer. Oh. Okay, might want to go back to where I was. This seems to be applicable for images. We've talked about bias before, bias, activation. So basically, this is almost like the building blocks of our neural network, right? So instead of having a linear unit, this is like another type of neuron that you can use, right? Recurrent layers. So I don't necessarily want to go in too much detail here because I think we'll be lost in things that we don't really understand straight away, but it's good to know that they exist, right? But let's take it easy. There's plenty of time to check them out. So there's lots of types of layers. The activation function. It turns out, however, that two dense layers with nothing in between are no better than a single dense layer by itself. Dense layers by themselves can never move us out of the world of lines and planes. What we need is something non-linear. What we need are activation functions. Okay, so let's try and digest this. First question is, what does it mean by having nothing between them? Does it mean that maybe I really don't understand? Nothing in between them. That's a bit uncertain. maybe it's talking about the network itself here. Maybe like when it says like if there's two layers like this, if there's nothing between them, there's no good use for it. Maybe. Now it's talking about an activation function that we can use to make sure that what we get is not just a line or a plane, because these are very predictable, right? And for that, the solution is an activation function. I don't know if I understand fully, but we'll see. With exercises, maybe that will become a bit more clear. Okay, let's go past this. Without activation functions, neural networks can only learn linear relationships. In order to fit curves, we'll need to use activation function. It's kind of a point, because we saw just now that a linear unit, for example, only is a line, like in a plane, right? In a 2D dimension, right? You never have things as perfect as that, right? So in this graph, right, the red dots are like the guesses. Let's say you're trying to guess a number, right? So the dots are basically the actual values that you get, and the line itself is trying to fit these results. So basically we draw this line to try and fit the actual data that we get. So these dots are actually given by the data. For instance, let's say you're trying to determine a position of an object, right? So imagine that the actual position of the object at any given time is where the dots are. If you're trying to find a function that basically fits all the results that you get, like all the actual data, because you've gathered all this data, taken note of all the positions, and then you decide, okay, I'm going to create a function that tries to fit all these results so that I can predict values. And the idea is, given that function, you basically just calculate what is the predicted position of the object. Okay, that's what's meant by fitting. Okay, so activation functions. Without activation functions, then basically you can only learn things that are linear. But if you have something like this, like a curve, then you need something nonlinear. So an activation function is simply some function we apply to each of a layer's outputs, its activations. The most common is the rectifier function, max 0x. So any negative values for max 0x are basically taken out. Any positive values are kept. So if x is negative, then max 0 of x is going to be always 0. Right, so that's the rectifier function. Applying the function to the outputs of a neuron will put a bend in the data, moving us away from simple lines. When we attach a rectifier to a linear function, we get a rectified linear unit, or ReLU. For this reason, it's common to call the rectifier function the ReLU function. Applying a ReLU activation to a linear unit means the output becomes max of 0 w times x plus b, which we might draw in a diagram like this. You know, it kind of reminds me of electronics, because there's also a rectifier function somewhere. So x is the input, this is the bias, okay, and then you get y. A rectified linear unit. So this is a symbol that means it's a rectified linear unit. Okay, stacking dense layers. Now that we have some non-linearity, let's see how we can stack layers to get complex data transformations. Okay, so let's see what this means. Inputs x0 and x1, the bias. Then these are rectified units, hidden. So rectified twice in a row. So these are become inputs for the next layer, and then they also get rectified. The layers before the output layer are sometimes called hidden, since we never see their outputs directly. Hidden also means because these are intermediate layers, right? So, and though we haven't shown them in this diagram, each of these neurons would also be receiving a bias, one bias for each neuron. Now, notice that the final output layer is a linear unit, meaning no activation function. Oh, I see. So at the end, there's no activation function. That makes this network appropriate to a regression task where we are trying to predict some arbitrary numeric value. Other tasks like classification, in this case image classification, I think, or some kind of classification where you have discrete values. When I say discrete, means like, for instance, when you are trying to predict a number, it's a continuous interval of numbers, let's say between 0 and 10, right? You get many values between 0 and 10. If it's discrete, then let's say true or false, that's a discrete. And in this case, is a classification function, because you're trying to determine if something is true or something is false. When I say true and false, they could be red, yellow, green. there's many different options. Okay, other tasks like classification might require an activation function on the output. Okay, let's go to the next section. I hope I can still do exercises. I think I can. The sequential model we have seen will connect together a list of layers in order from first to last. The first layer gets the input and the last layer produces the output. This creates the model in the figure above. So let's see if I understand this code. So we have a sequential carriers.sequential. So first dense layer that we have has 4 units. Yeah, this is the one. We're defining 1, 2, 3, 4. Then activation is relu, which means is the rectifier linear unit. Then the input shape is 2, because the inputs are 2. So 1, 2. Okay. Then we have another layer. The next layer has 3 rectifier linear units, 3 neurons. And then finally, the last layer has only 1. And it's using the regular linear unit. Okay. Be sure to pass all the layers together in a list, like layer, 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 and so on, instead of as separate arguments. I'll try and remember that. I hope I don't forget. To add an activation function to a layer, just give its name in the activation argument. Time to get our hands dirty.